Okay, we're going to start in chapter 11 here. The entire chapter is a study of right triangles. This is an extremely important chapter in preparation for trig next year or pre-calculus. So anyway, without any further ado, let's get started. The first section, proportions in right triangles. I'm going to talk about the three little bears with these triangles that you see here in the diagram. Before we do that, this first slide is a definition review of an altitude. Well, an altitude is just simply a line segment drawn from the vertex of a triangle down to the opposite side, and it's perpendicular. So in any triangle like this small one here, I could draw three different altitudes. And the main one that we're going to talk about, though, in this particular section is this guy here. This is a right triangle, and we're going to talk about, in the right triangle, the altitude drawn from the right angle to the hypotenuse. With that being said, here we go. Our first theorem deals with that exact diagram. It basically is saying that if we have the altitude AO drawn in here, that there are three triangles that are similar. And we're going to refer to those three triangles as the baby bear, the mama bear, and the papa bear. So if I look at this particular diagram, same as above there, and take this first triangle and rotate it, I'm going to move it up here in position, and we're lovingly going to call this little guy the baby bear triangle. The blue one here that forms when I drop that altitude in, I'm going to take that and move that up here into position, and we're going to call that guy the mama bear triangle. And then finally, the large one, or the original big triangle that we drew the altitude in, we're going to refer to this as the papa bear triangle. And if I take this and flip it and rotate it around like I'm doing, you can see that those three triangles do appear to be similar. Same shape, not the same size, but they are the same shape, making them similar. So, keeping the wording easy, basically with that little illustration on the bottom, I'm just taking this statement that's written right here, and I am basically just showing you the three triangles are similar and rotating them around just to make it easier to see that. So when you see this diagram, think of the three little bears, the baby bear, the mama bear, and the papa bear. Those three triangles are all similar to each other. Continuing a little bit of review here, we talked about a geometric mean in the previous chapter. A geometric mean is a proportion like we have here where the means repeat as the same number. So to quick review, find the geometric mean between 8 and 12. So I would set this up as a proportion with the geometric mean, or x, repeating, because we're asked to find the geometric mean. And then it repeats between the extremes of 8 and 12. And then you would just solve that, and you'd say x squared is equal to 8 times 12 is 96. And to solve that, you take your square root, and the square root of 96, the perfect square in there would be 16. So you would end up with 4 radical 6. Much like the second one here, it says 10 is the geometric mean. So in this particular one, 10 being the geometric mean means that 10 repeats as the means. And 10 is the geometric mean between 5 and what other number? Well, since we don't know, I'm going to call this x. So there's my proportion. 5x is equal to 10 times 10 is 100. And x ends up equaling 20. All right, so just a little review there of geometric mean, which is going to be useful because in the next theorem that we get into, we're going to be talking about a geometric mean within that theorem. Okay, here we go. In this particular theorem, it says that the altitude to the hypotenuse of a right triangle is the geometric mean between the segments into which it divides the hypotenuse. So if I look at this particular diagram, it says the altitude is AO. Well, AO is a geometric mean. It repeats between the two segments of the hypotenuse. So when I drop this altitude in here, it divides the hypotenuse into two segments, and for a lack of a better name, I'm just going to refer to them as segment 1 and segment 2. So basically, what this is telling me is that the altitude is the geometric mean, and it repeats between the two segments of the hypotenuse, so between segment 1 and segment 2. Well, with that, that basically this whole theorem can be proven easily as a consequence of the three little bears theorem we talked about earlier. I'm not going to go into detail there, but it's just a proportion that's set up because of those three little bears and those triangles being similar. Let's take a look here at our first example of this particular type of problem. It says here that find OC, so OC is going to be my unknown x, and it's given me that BO is equal to 4, and also that AO is equal to 8. As I'm doing this, I keep the theorem in my head, okay, and I look, can I use this particular theorem? And it says the altitude is a geometric mean between the segments. And that's what I keep in my mind. And I literally don't necessarily memorize this formula. You can if you'd like. I think, well, in this diagram I do. I've got the altitude. So I know, the altitude 8 is a geometric mean. So I put it in the place of where the geometric mean would go. It is a geometric mean between the segments of 4 and x. So here we go. 4x ends up equaling 64. And the value of x in this case is equal to 16. So I look at my next problem here, and it gives me some more information. I'm going to erase that and clean the diagram up so we can use it again. It wants me to find, in this case, AO, so my unknown here is my altitude, and it's giving me that the length of BO is 3, and the length of OC is 27. Now, if that's 27, that means that this segment right here is a length of 24. Okay, so don't mistakenly use that 27 in your proportion, because it says, as I said earlier, the altitude, which in this case the altitude is x, it is the geometric mean between the two segments. Well, the two segments of the hypotenuse in this case are 3 and 24. So as we solve this proportion, the product of the means is equal to x squared, equal to the product of the extremes, which is 72. As I take my square root here to solve, x ends up equaling, largest perfect square in 72 is going to be 36. So we're going to get 6 and radical 2. Now, this wasn't too hard because in these particular problems, we knew we were going to use this theorem. In the future, when I look at diagrams, I've got to look at the diagram and decide, do I use this theorem? Do I use another one coming up here in the future, or do I use the three little bears that we talked about earlier? So in my mind, I look at the diagram, the altitude's a geometric mean between the segments, and I see in my diagram I have all those things. So yes, I'm going to use that particular theorem or proportion to solve. In our next theorem, nothing really noteworthy that you have to take here, but you need to understand what a projection is. To keep it simple, the projections, what we're doing is really renaming this segment 1 and segment 2 from the previous slides. And a projection is basically for this particular leg of Papa Bear, AB. If the sun is shining down on my Papa Bear triangle, Papa Bear's triangle would project a shadow on the ground, which is segment BO. So segment BO is the projection of AB. So I'm going to label BO as such. It's a projection. And then also, Papa Bear doesn't have one leg, but Papa Bear has two legs. That's a good thing. That means he can walk. Anyway, Papa Bear triangle with the second leg of AC has a projection of OC because of the sun shining down on this leg. The shadow it would cast on the ground is segment OC. So this here is also a projection. So BO is a projection of segment BA, and OC is a projection for OC, or of AC. We need to know those terms because as we get into the next theorem, it talks about exactly that. It says each leg, and once again, I'm going to highlight, I remember wording to help me remember these theorems. It says each leg of a right triangle. So I remember that the leg, and when we're talking about the leg, we're talking about the leg of Papa Bear. We're not talking about baby or Mama Bear. So we're talking about the leg of Papa Bear. The leg in this theorem says it is a geometric mean between the hypotenuse and its projection on the hypotenuse. Okay, so if I take a look at that, what's that really stating? With A's, B's, and C's, well, the first leg of Papa Bear is AB. So the leg AB here is a geometric mean between its projection. Well, the projection of AB is this shadow it would cast here, which is BO, between the projection and the hypotenuse of the whole thing here of BC. And this theorem gives us actually two different proportions because Papa Bear has two legs. Papa Bear's second leg is also a geometric mean. So here, this second leg of AC is a geometric mean between the projection of OC and the entire hypotenuse of BC. So here we go. I don't really remember the letters. I remember the words. The leg is a geometric mean between its projection and the hypotenuse. And also, the other leg is a geometric mean. And it's a geometric mean between its projection and the hypotenuse. So when I'm remembering these, I remember that in my mind. I don't necessarily memorize the formulas. You can if that's helpful for you. Let's take a look here at our first example. With the information that's given, I've got BO is a length of 5. I've got BC, the whole hypotenuse, I'm going to label that down here, is 16. And we need to find AB. Now, how do I know which theorem I'm looking at? Well, the other one I talked about the hypotenuse. In this diagram, the hypotenuse is not labeled with a number or a variable. So that's a pretty good chance I'm not using the idea that the hypotenuse is a geometric mean between the two segments of the hypotenuse. So the altitude, the geometric mean between the segments, not going to work here. But the leg of x being a geometric mean between the projection of 5 and the entire hypotenuse, which is 16, that is going to work because in this proportion I've only got one unknown. So my geometric mean, x times x is x squared when I take the product of the means, is equal to 5 times 16. And sometimes in math, I like to work smarter and not harder. I'm not even going to multiply those because I know I'm taking the square root. And why multiply it when 16 is already a perfect square? I know that the square root of 16 is going to give me 4, and the square root of 5 we don't know, so that's going to stay inside my radical. Taking a look here at the next example, I'm going to find the length of OC. So here's my unknown, x. And I know that BC is 20. That's my entire hypotenuse. And I know that AC is a length of 15. So once again, I look and figure out what I'm trying to do, and oh, they give me a leg, and I know, oh, the leg, it's a geometric mean. So I start writing my proportion. The leg of 15 is a geometric mean between the projection of that leg is OC, which is the length of X, and the entire hypotenuse of 20. So here we go. We've got 20x is equal to 225. And when I divide by 20, x is going to equal 11.25. Okay, onward here. Taking a look at our optical illusion for the day. It may not appear that way, but segment AB is equal to segment AC. Guys, as I said earlier in the video, please take time to look at those examples. Rewind if you need to. Make sure you understand what's going on and take time to memorize what these things say. So in my memory, I have for this one, oh, the leg is a geometric mean between the hypotenuse and its projection. Okay, and then for the other theorem here, I have the altitude is a geometric mean between the two segments of the hypotenuse. Go over that in your mind over and over again and memorize that. So when you look at a diagram, you got to know what those things mean, but it will be helpful in the process of trying to use these theorems on problems that you're going to get. Have a great day and good luck, and come to the chat if you have questions.